In the previous lecture, we introduced a proposed mechanism for enzyme catalysis, and the mechanism looked like this. The enzyme interacts with the substrate, forms an enzyme-substrate complex, and this is a fast step. And then the second step, the enzyme-substrate complex falls apart, producing the enzyme and the product. And here, of course, the enzyme is the catalyst. So remember, that would be that it becomes involved in step 1 and then reappears in step 2. And the enzyme substrate complex would be the intermediate because it's produced in step 1 and then quickly is used up in step 2. For more than 100 years now, many enzyme catalyzed reactions, and even those with different mechanisms than the one we're proposing here, have been described by what has come to be known as Michaelis-Menten Kinetics. In 1913, Leonora Michaelis and Maud Menten published a paper having to do with the decomposition of table sugar into the two simple sugars fructose and glucose by virtue of the enzyme invertase. You can see the reference here, 1913. The importance of this enzyme substrate complex in the mechanism was not Michaelis and Menten's original idea, but they did a much more complete analysis of this reaction, and subsequently in the last century, it's their names that have been on this template for describing many enzyme catalyzed reactions. Now, the original paper was in German, but around the 100th anniversary of their contribution, there were some translations of this paper. Reference 2 is one of the translations, which we'll use in this lecture. What we're going to do is examine this reaction that they looked at and look at some of their original data and see how the data that they took is consistent with this mechanism that we've outlined. The reaction that they actually looked at could be written like this: sucrose, which is here the substrate, and of course sucrose is a disaccharide, table sugar, is converted into glucose and fructose. These are the products of the reaction. In our mechanism, we just show one product, P, but of course there could be more than one, and here there is more than one product. Glucose and fructose are both monosaccharides, and a mixture of these two is commonly referred to as invert sugar, which is what you'd find in honey and some candies that you probably still enjoy. The enzyme is invertase. The reaction was carried out at pH 4.7. They did this by using equal concentrations of acetic acid and sodium acetate. That type of solution is called a buffer, and we'll learn more about that in some later modules. Now, based on some earlier work by Victor Henry, here's a reference, and some others, Menten and Michaelis knew that this enzyme substrate complex was really important. In addition, those previous works revealed some other things about this reaction. One of them was it really did require a consistent control of the solution pH. So Michaelis and Menten, as I mentioned here, took care of this by running all the reactions in an acidic buffer, pH 4.7. Another thing that was known from earlier work was the annoying problem that the products of glucose and fructose, when they formed, started to inhibit the reaction. In other words, the reaction would slow down as products formed for the reason that the products were actually interfering with further reaction. So Michaelis and Menten addressed this by simply measuring the initial rates. In other words, just the first few percent of the reaction before this inhibition took over. And you should remember that earlier in this module, we introduced the method of initial rates as a way to find the rate law of a reaction. So again, we're going to use some original data from the 1913 paper to show how they use their data to formulate an experimentally determined rate law. Well, here's some original data from that paper. And for this particular run, the concentration of sucrose, the substrate, is 0.0833 molar. The total concentration of enzyme, or the total concentration of invertase, is, we don't know. That seems rather odd, but I could not find a concentration in the translated paper. We do know that, or pretty sure that it was held constant. This total enzyme concentration will turn out to be important later. The total enzyme concentration is the concentration of the enzyme-substrate complex at any time plus free enzyme. The pH, of course, is 4.7. They did carry out the reaction at 25 degrees C, and they monitored what's called the change in optical rotation in degrees as a function of time in minutes. So here's the data on the y-axis, change in optical rotation, time in minutes, and we can see the data here as the optical rotation changes over time. There was more data taken at longer time, and it's not shown here in my plot. Well, recall that in a lab, you really need a handle on how to track the concentration of reactants or products with time. And interestingly, here what you'd expect to see is the concentration of a product, say, with time. It's growing in with time. But we don't have a concentration. We have a change in optical rotation. Well, what is the optical rotation? This is something you'll learn about when you talk about carbohydrates if you sign up for organic chemistry. So for now, we're just going to say this is our handle, change in optical rotation, on the concentration of here the products. Well, how would we determine the initial rate for this experimental run with the sucrose concentration 0.0833? Well, what we would do is just look at the first few percent of the reaction. So in this plot next to the original data, what I've done is I've just plotted the change in optical rotation per unit time just to under 100 seconds, and I fit a straight line to this, a trend line in Excel. This is an initial rate because it represents less than 10% of the total reaction, because the reaction actually went on for about 1,000 minutes. And what I have here is the equation of the line. You'll notice that the slope is 0.0297, and the y-intercept is not listed because the y-intercept here is 0, because when I plotted this, I told Excel to make sure the line goes through the 0, 0 point. In any event, we can get the change, or the rate, reaction rate, from the slope. So what we'll say here is the initial rate of this reaction from the slope of this line is 0.0297. So now we have one initial rate measured when the initial substrate or sucrose concentration is 0.0833 molar. You might note that 0.0833 molar is listed twice here. It's because in the data table that I used from the 1913 paper, they ran this reaction twice. So on the next slide, we'll fill in the rest of the data. So here's the rest of the data. I determined all of these initial rates in the same way as I did on the previous slide for the 0.0833 molar concentration. So here are all my initial rates with initial sucrose concentrations. And if we plot that, we get a plot that looks like the ones we were just talking about. But remember, this is a different plot. This is initial rate as a function of the initial concentration of substrate. And there's some strange behavior here. You'll notice that when the substrate concentration is lower, the rate seems to be pretty sensitive to the concentration of substrate. In other words, as the substrate concentration increases, the rate increases pretty dramatically. So we say that at lower concentrations of substrate, the rate's strongly dependent on the substrate concentration. But as the substrate concentration gets higher, the rate becomes less and less dependent on S. And in fact, it appears to approach a maximum where it seems to become completely independent of the substrate concentration. So that is, at high concentration of substrate, the rate becomes zero order in substrate. Now recall from a previous slide that Menten and Michaelis relied on that previous work of Victor Henry to hypothesize that some sort of enzyme-substrate complex was really important here to understanding these results. So they needed to derive a rate law that kept in mind the importance of this enzyme-substrate complex, but also was consistent with these experimental results, these strange results, where the rate seems to be dependent on the substrate concentration pretty strongly at lower substrate concentrations, but becomes independent of substrate concentration at higher concentrations. So let's see what they did. This is a reproduction of the plot from the previous slide, but there are some changes which you've probably already noticed. The initial rate we are now calling the initial velocity, which we can label capital V sub 0. The maximum rate is now the maximum velocity, Vmax. Just keep in mind that when describing enzyme kinetics, biochemists and biologists typically refer to rate as velocity, and we'll follow that custom here. Michaelis and Menten found that the rate law expression that would fit this data quite nicely is this right here, where the initial rate equals Vmax times the substrate concentration divided by the sum of what's come to be known as the Michaelis-Menten constant plus the substrate concentration. The green dotted line here is the fit of this equation to the data. Seems to fit it pretty well. Well, let's look at this rate law and see how it works. At very low substrate concentration, when S is very low, we might be able to say that the denominator here is simply the Michaelis-Menten constant. In other words, Km plus this very low concentration of S is just equal to Km. If that's the case, you'd end up with an expression here where the initial rate is dependent on the first power of the substrate concentration. In other words, the rate is first order, the reaction's first order in S. Now at high concentration of substrate, the Michaelis-Menten constant might become much, much less than the substrate concentration. So we could say that in this denominator that Km plus S is just approximately equal to S. If that's the case, the S cancels out in the numerator and the denominator, and you have an expression that seems pretty reasonable that the initial rate is equal to Vmax. In other words, at higher substrate concentration, the reaction approaches zero order in substrate. The green dotted curve, which I said was a fit to this data, is a fit using a Vmax of 0.038 and a Michaelis-Menten constant Km of 0.020. So we now have an experimental rate law for this enzyme catalyzed reaction. Now what? Well, we're tasked with showing that this is a viable mechanism for our reaction. And we have an experimentally determined rate law. Does this mechanism give us this experimentally determined rate law? Well, if you recall from lecture 5, that a proposed mechanism like this one would be valid if two things apply. The first is that it correctly adds up to the overall reaction. Well, I think we've passed that test because in our mechanism, the enzyme-substrate complex intermediate and the enzyme cancel out. So overall, we have substrate going to products, sucrose going to glucose plus fructose. So we've passed the first test. That makes sense. The second is that the rate law derived from this mechanism needs to give the experimentally determined rate law. In other words, the mechanism needs to correctly predict the experimentally determined rate law. Well, we've identified the second step as the rate determining step, and so our proposed mechanism would then predict the following rate law. Based on this second elementary step, rate determining step, the overall rate, velocity, would be equal to K2 times the concentration of the enzyme substrate complex. Well, you see we have a problem right off the bat. This predicted rate law does not match the experimentally determined rate law. So the question is, should we just trash our proposed mechanism? Well, let's hold on to it for a little bit and try a few things. First of all, you need to realize that the concentration of intermediates in reactions are often challenging to measure in real time. And so maybe we can find, without cheating too much, a concentration term from our proposed mechanisms to substitute in for ES. And maybe that will miraculously give us this experimentally determined rate law. Doesn't look good right now, but let's keep going. We probably are going to have to put some conditions or constraints on our proposed mechanism to give us a chance to make this work. So here's again, our proposed mechanism, the experimentally determined rate law, and from our proposed mechanism, we get this for a rate law. Let's start by remembering that at any time in a reaction, the enzyme exists in two forms. We've already mentioned this. And the total enzyme concentration at any given time, ET, is going to equal the concentration of free enzyme, that's enzyme with no substrate bound, plus the concentration of any enzyme substrate complex. From the two elementary reactions, step 1 and step 2, we could write more expressions. So from step 1, the rate of formation of ES is equal to K1, that's the rate constant going to the right, times the enzyme concentration times the substrate concentration. That's one pathway for the formation of the enzyme substrate complex. From steps 1 and 2, we can write that the rate of breakdown of ES, the enzyme substrate complex, is equal to K minus 1 times the concentration of ES, that's this reverse reaction, plus K2 times the concentration of ES. All we're saying here is that there's one pathway for the formation of ES, and there's two pathways for the destruction or the breakdown of ES. ES going backwards here, ES going forwards in step 2. Now we're going to make an important assumption. This is one of the conditions we're putting on our mechanism, and we're going to say that the rate of formation of the enzyme-substrate complex equals the rate of breakdown of the enzyme-substrate complex. Now, this does not mean that the enzyme-substrate concentration is 0 during the reaction, but rather it reaches a steady, constant concentration because it's being formed as quickly as it's breaking down. We say it's reached a steady state and then its concentration stays relatively constant through most of the reaction. Now in math speak, we would say this means that the rate of change of ES with time is 0. It's not changing over time, it's staying constant. Chemists call this the steady state approximation, and this is a widely used tool in chemical kinetics. It follows then that the rate of formation of ES, which is expressed right here, is equal to the rate of breakdown of ES, which is expressed right here. So these two expressions are equal to each other, and we can do a little substitution here because from our expression up here, the concentration of free enzyme is going to be equal to the total concentration of enzyme minus the concentration of enzyme substrate complex. So we've just expanded our expression. Now our next task is to solve for ES, because remember, we started out trying to see if there's any way we can substitute an expression for ES in here and get rid of ES. In other words, substitute it with something that's equivalent to that. Well, let's see how we do. First of all, let's do the algebra necessary to solve for ES. So from the previous slide, we have this expression. What I'm going to do is just expand the left side by multiplying through by K1. I'm going to try to collect all the terms with ES on it on one side. So I'm going to bring this term over here on the left side by adding it to both sides. I'm going to factor out the ES term, so we have that. And I'm going to solve for ES. So now we have this expression here. Then we'll just do something that appears to be a little random. We're going to divide both top, the numerator, and the bottom, the denominator, by K1. If we do that, K1 ETS becomes just ETS. And down here, if we divide through by K1 and leave K minus 1 plus K2 together, we'd have K minus 1 plus K2 over K1 plus K1S divided by K1, which is just S. And if we substitute this ES expression in for that, we have an expression where we have no more ES. Remember, we wanted to get rid of that. And so we can say our rate, or our velocity, is equal to K2 times our expression for ES. We'll let this group of constants be the Michaelis-Menten constant. So now we have velocity equals K2 ETS over Km plus S. The experimentally determined rate law is right here, so we're very close to getting our proposed mechanism to give us a rate law equal to the experimentally determined rate law. We can do better. So from the previous slide, our proposed mechanism has given us this rate law, which we said is pretty close to the experimentally determined one. Since reactions were, and typically are, carried out by using a large excess of substrate, meaning there's way more substrate than enzyme, and our proposed mechanism states that the formation of ES from E and S is fast, we can justifiably assume that at any particular time in the reaction that this will be true. The total concentration of enzyme is equal to the concentration of the enzyme-substrate complex because there's so little free enzyme. We now have the concentration or the velocity equal to K2 ES times S over Km plus S. Now you might ask, didn't we just go backwards? We were trying to get rid of ES out of this expression. Well, hang in there for a second. The overall reaction rate, remember, is determined by step 2. That's the rate determining step. The rate expression from step 2, remember, is K2 times ES, and that represents the maximum rate that the reaction can achieve. So we can make the assumption that K2 times ES is actually equal to Vmax. We now have rate velocity equals Vmax times S over Km plus S. We now have a match. We've gotten our proposed mechanism to give us a predicted rate law which matches the experimentally determined rate law, as long as some assumptions are made and certain conditions are met. So let's summarize on the next slide. Our proposed mechanism here for this reaction is valid because it correctly adds up to the overall reaction and it correctly predicts the experimentally determined rate law, but with the following conditions. The reactions run with a large excess of substrate. At any given time, most of the enzyme is in the bound form. The formation of that bound form, or the enzyme-substrate complex, is fast and rapidly reaches a constant concentration. In other words, we invoke the steady-state approximation, and that the second step in our mechanism is the rate-determining step. Now recall from lecture 5 that just because our proposed mechanism meets these criteria, it doesn't mean that there aren't other mechanisms that would also give us the experimentally determined rate law. However, the above mechanism has become the pretty much de facto starting template when we're talking about enzyme catalyzed reactions. In other words, we say a lot of them, not all of them, but a lot of them follow Michaelis-Menten kinetics. So what now? Let's look at an accepted alternate method of extracting the values of Km and Vmax for an enzyme catalyzed reaction. It's called a Lineweaver-Burke plot. A Lineweaver-Burke plot simply linearizes this rate law. Let me show you what I mean. If we take the reciprocal of both sides, that seems pretty easy. 1 over V0 equals Km plus S over Vmax times S. We flip over both sides. If we expand the right-hand side, in other words, write Km over this denominator plus S over this common denominator, we find that in this part of the expression now, S cancels out, and we get this expression. If we factor out the S, in other words, write it as 1 over S, we get this expression, and this has come to be known as the Lineweaver-Burke equation, and it's the equation of a straight line. It's also called a double reciprocal plot, because we're plotting the reciprocal of the reaction velocity versus the reciprocal of the substrate concentration. Here's a Lineweaver-Burke plot in a way it typically looks. The slope here turns out to be Km over Vmax. The y-intercept is 1 over Vmax. So from those two things, you can get both the Vmax and the Michaelis-Menten constant. Turns out that also the x-intercept can give you the Michaelis-Menten constant. And that's because the x-intercept is, of course, the value of x when y is 0. If we put our Lineweaver-Burke equation in here and set y, which is 1 over v0, to 0, and just substitute an x in for 1 over s, what I've done here is I've solved for x. And you can look at this and see if you agree with my algebra, but it seems like I come out with the value of x there being equal to minus 1 over km. So let's plot our data, the invertase data from the original paper, as a Lineweaver-Burke plot, and compare the km and Vmax values we get with those we got from the 2-parameter fit. So here's our data table: substrate concentration, sucrose, initial velocities, and what I've done is I've plotted here 1 over s and 1 over the initial velocity. And of course, the 0, 0 point would be undefined there. In any event, here's our Lineweaver-Burke plot. Our slope is 0.5073. Y-intercept's 26.8, pretty good fit, and r squared of 0.997. So here's our slope, our y-intercept, and we can calculate from the y-intercept that the Vmax is 0.0373. We'll use that and the value of the slope to get a value of the Michaelis-Menten constant. If we get the Michaelis-Menten constant from the x-intercept, we'd have to know where the x-intercept is. I actually used I zoomed in on this plot, used a millimeter ruler to create a scale, and got an x-intercept of minus 52.1. And from that, I get a km of 0.0192. If I average those two, we can say that the Michaelis-Menten constant is around 0.019. So in summary here, the Lineweaver-Burke plot gives us a Vmax of 0.037 and a km of 0.019. From the curve fitting, we got 0.038 and 0.020. That's pretty good agreement. Now you can go ahead and notice that I have been a little loose with units here, and I've been a little loose with significant figures, but I think we could all agree that 2 sig fig seems pretty safe. One last thing, you might wonder how you could compare one enzyme catalyzed reaction to another as far as how efficient that reaction is. Those comparisons can be made by calculating for each reaction something called a specificity constant. It's the rate constant for the rate determining step divided by the Michaelis-Menten constant. The Michaelis-Menten constant has concentration units. kcat is a first order rate constant, which means it would have units of 1 over time, like per second or per minute. This rate constant's often called the turnover number, and it's an interesting number. It represents the number of substrate molecules converted to product per unit time on a single enzyme, assuming, of course, that the substrate is in excess. So here's a table from a textbook that shows some specificity constants in units of per mole per second for several enzyme catalyzed reactions. And the specificity constants increase going down the table. In other words, the reactions become more efficient. So you'd say that the catalysis of the reaction where these two amino acids are broken into these small protein fragment is broken into its two amino acids, and the catalyst is pepsin, is not nearly as efficient as the enzyme carbonic anhydrase working on the reaction of the transformation of bicarbonate to water and CO2, because the specificity constant is much higher for the carbonic anhydrase. So our final question here is, where would the specificity constant of our invertase catalyzed sucrose to glucose plus fructose reaction fall on this table? Well, let's find out. Let's try to calculate the specificity constant for our reaction. kcat over km. We said from our Lineweaver-Burke plot that km is 0.019. For our proposed mechanism, kcat would be simply equal to K2. Remember, kcat is the rate determining step in the reaction. So from slide number 10, we might be able to get what K2 is, because K2 times the concentration of the enzyme substrate complex equals Vmax. So K2 should be Vmax over the concentration of the enzyme substrate complex. We have Vmax, but we don't have the concentration of the enzyme substrate complex because we don't know what the concentration of the enzyme was in the Michaelis-Menten paper. So how do we get out of this dilemma? Well, luckily for us, in 2014, a paper reported, carried out this reaction, our invertase reaction, monitored the concentration in a different way than Michaelis-Menten did, came up with a K2 of 367 per second and a Km of 0.064 molar. That'll give us a specificity constant in the units that we can compare with our other reactions here. We get a specificity constant of 5.7 times 10 to the third. So in other words, our invertase reaction is comparable to some of the lower efficiency enzyme substrate combinations on our list. Well, what are the take-home lessons here? First of all, many enzyme catalyzed reactions follow Michaelis-Menten kinetics, which shows a nonlinear dependence of initial rate on initial substrate concentration. The experimentally derived rate law, which describes this behavior, is called the Michaelis-Menten equation. We can linearize this to create a Lineweaver-Burke plot to more easily get the Vmax and the Km. The overall reaction mechanism that gives a rate law consistent with this is right here with the rate determining step. The second step, this reaction mechanism only works if we assume the total enzyme concentration is equal to about the enzyme substrate concentration. In other words, all the enzyme is pretty much bound at any given time, and we invoke the steady-state approximation. This also assumes a rapid formation and buildup of the ES complex, with the concentration staying relatively constant while waiting for this second rate determining step. And the efficiency of various enzyme substrate combinations can be compared by calculating their specificity constants. And for our model reaction here, kcat is simply equal to K2. Just keep in mind, variations from our model mechanism can also show Michaelis-Menten kinetics.